So for this video, what we're going to do is look at a question that combines some of the things that we've been talking about. So this question will involve an enthalpy of reaction as well as an enthalpy of a phase change. And so this is one from the back of your in your textbook from the back of the chapter that I thought was a really interesting one. So the question is, how much glucose, given this formula C6H12O6, this is a sugar that's used inside your body to power your cells. And it has this molar mass that I just calculated for you in advance, so we don't need to calculate that, 180.2 grams per mole. But how much glucose needs to be metabolized to completely evaporate 1 gram of water at 37 degrees Celsius, given some information? Specifically, the delta H combustion of glucose. You'll see this often with enthalpy values for reactions. We sometimes have specific types of reactions we're talking about, and so we put that, so COMB is short for combustion. You'll see that often delta H combustion. You may see delta H of other types of reactions as well. But the enthalpy of combustion of glucose is negative 2803 kilojoules per mole. The other thing that's relevant here is that the enthalpy of vaporization of water is 40.67 kilojoules per mole. So we're going to assume, so let's, I want you to pause the video and think about how you're going to approach this problem. So hopefully you took some time to think about that. Think about what we need to figure out about this question. I'll tell you how I'll approach it. So one thing we can do is, in the previous example with enthalpy of combustion, we use the enthalpy of combustion to find, or we use the number of grams to find an energy. In this case, what we know is the amount of, or what we need to figure out is how much energy, we can figure out how much energy we need, and then use that to get our grams of our reactant, in this case glucose. So we're going to be going a little bit backwards. But the first thing is that we need to know, well, how much energy do we need in the first place? Once we have that, this problem is pretty straightforward, but we have an extra step here. And the energy we need is going to be based on the fact that we have 1 gram of water. We have like a drop of water here. And that starts as a liquid, and it's going to turn into a gas. Now, there is an assumption we have to make here. We have to assume that it just says it's going to evaporate, so we're not heating it and boiling it. And also, we have to know what the enthalpy of vaporization is. Now, the enthalpy of vaporization that I gave here is for water at 100 degrees Celsius. And so the assumption we're going to make is that it's pretty close to the same at 37 degrees Celsius. So we can think about this enthalpy of vaporization is going to apply to this process. So 40.67 kilojoules per mole. So the question is, how much energy is required to do that? So that once we know that amount of energy to do this process, we can plug that into here, and that's the concept of how we're going to approach this question. So now let's actually go ahead and do that. So we know we have, let's figure out how much energy we need. We now have 1 gram of H2O, but our enthalpy is given in terms of moles, so we're going to have to convert this to moles. So that'll be 18 grams of water for 1 mole. All right, so let's go ahead and just calculate that real quick. And you can use more significant figures. I'm just using 18, but it's like 18.0 something. So 0.556, we'll round that up. So that's 0.55, I'm missing a 0 there. 0.0556 moles of H2O. Make sure I have the right number of zeros. Yeah, there's a 0 at the beginning there. So then we need to, now that we know how many moles, the question is how much energy does it take to evaporate that many moles of H2O? So that'll be Q. Q for our vaporization is going to be equal to our number of moles, 0.0556 moles, times our enthalpy of vaporization. So we're just taking that from up here. So that's 40.67 kilojoules per mole. Our moles are going to cancel, and we'll get a unit of energy, kilojoules, at the end. And let's go ahead and do that. So we have 0.0556 times 40.67 gives us 2.26 kilojoules of energy required. So now we're going to use our enthalpy of combustion that we have for glucose to go backwards from that. So we know we need keep doing that. We know we need 2.26 kilojoules of energy. And so we can use our enthalpy of combustion to go from that to know how many moles of glucose need to combust to produce that much energy. So we're going to use our enthalpy of combustion here. And so we need the units to cancel. So our kilojoules are going to go on the bottom. And for our purposes, we're going to ignore the sign. So the enthalpy of combustion is negative 2803. We'll ignore it in the sense that we know that all the energy from the combustion is going into the water. These have equal and opposite signs, the Q values do. So that's why the negative sign disappears. Right, but 2803 kilojoules per mole of glucose that combusts. That'll give us a value of number of moles of glucose. So 2.26 divided by 2803 gives us a value of 8.06 times 10 to the minus 4. Moles of glucose. And we can see that's not very much glucose. It's only 1 gram of water, so we're not going to need tons of sugar to power this. And then what we want to do then is multiply that to get by the molar mass to get grams. So 8.06 times 10 to the minus 4 moles of glucose. And then multiply by, for every mole of glucose, we have the molar mass up at the very top of the question here. Come back up here. 180.2 grams per mole. All right, so now we can do that last calculation. So I still have the answer from the previous one here, so I'm just going to multiply by 180.2, and that gives us 0.145 grams of glucose. All right, so I think this is a good question that exemplifies that we can combine these ideas of heating, phase changes, along with enthalpies of reaction to get some more interesting questions. And so, I encourage you to make sure you understand the steps that I went through in this example problem, and we're going to practice with this with some additional questions as well. But that's the basic idea. We have enthalpies that are associated with reactions. We can use those to get quantities, in this case, how much glucose do we need to metabolize or burn, assuming all of the, you get all the energy out when you metabolize it that you would in a combustion reaction. And we can also relate that to a phase change involving water. So we'll continue to practice with this, and I'll see you in class.